In the next program, the triangle is rotating, the camera can be panned and zoomed, and we can interactively define a polyline, or also called line strip. Of this interactive program, first I show you how it works. So we have a rotating triangle with smoothly changing color in it. And additionally, we can specify a polyline by clicking on different points on the window. The clicks are connected by line segments. Here are the different commands. So, for example, we can manipulate the camera by panning the camera or zooming the camera out or zooming in. And additionally, we can add the translation to this line strip. For example, we can push it to the left or to the right, or down or up. The important message is that no matter how we change the camera transformation or the transformation of the polyline, any additional click will add the point that is right below the cursor. So we click further so we can continue building up this polyline. Let us start the discussion at the end of the file where event handlers can be found, because they are strongly related to the physical events happening on the user interface. Virtual world contains two objects, a triangle object and this line strip object. These are global variables because they are constructed in the onInitialization function, but they will also be used in the display. Let's see the onInitialization. First, the photograph is set in the application window, that's the viewport. It's also possible to define the line width in OpenGL with this GL line width function. Then we create the two objects of the virtual world, calling their create member functions. You may ask, why don't we create these objects in their constructors? Now the answer is that creation requires OpenGL functions, because with OpenGL functions it is possible to define the VAO and the VBO corresponding to a particular object. So if creation was a part of the constructor of these objects, as these objects are global variables, their constructors will run before the main function is even started. Remember that OpenGL is initialized in the main function. So if creation were included in the constructor, then we would call OpenGL functions before their initialization, and this is not a healthy approach at all. So there are basically two solutions. Either these objects are created dynamically with a new operator, or we separate the construction where only OpenGL independent member functions are initialized, and the real creation with the help of OpenGL, for which we can implement a create function like here. The GPU program is also created, and we print out the possible user commands. On display is called when the window has become invalid. Here we specify the clear color, clear the screen, not only that part of the screen where color information is stored, but also that part in which we store the distance values of objects whose color is written into the frame buffer. After clearing the screen, the triangle and the line strip is rendered, and for double buffering we force OpenGL to swap the two buffers, so the result will be seen by the user. In case of keyboard events, the commands are separated according to the pressed key. The user can pan the camera, can zoom the camera, or can add transformations to the line strip object. Whenever we modify the camera or the properties of one of the virtual world objects, the state of the virtual world changes. Therefore, we should re-render the scene immediately to immerse the user into that virtual world. So that's why we invalidate the application window, and as a result, OpenGL and GLOT will force this on-display function to run, which will restore the screen according to the new state of the virtual world. When the user presses a button on the mouse, the input coordinates given in the pixel coordinates of the operating system are transformed to normalized device space, and with these normalized device space coordinates we call the add point function of the line strip object. So the click is built in the line strip. And again, we invalidate the window in order to get the window to be redrawn. When time elapses, the elapsed time is computed in seconds, and then the triangle's animate function is called, which will update the state, the animation parameters of the triangle, and finally we will redraw the screen with the new state. Then let's go to the beginning of this program. It has a vertex shader and fragment shader. The vertex shader has one uniform variable, the model view projection transformation, that is responsible for transforming the object to normalized device space. This vertex shader assumes that in input register number 0, the vertex shader can find the position of the vertex, and in input register number 1, it can find the color of the same vertex. This vertex shader calculates a single output color and passes it with the transformed coordinates to the fixed function pipeline of the GPU. Now, the output color is just a copy of the input color. The output position is the transformed version of the input position. So we extend the two-dimensional XY Cartesian coordinates with a 0 in order to place it in 3 dimensions, and we add the 1 in order to make the Cartesian coordinates to homogeneous coordinates, and finally multiply it by a 4x4 matrix. The fragment shader gets the color variable, more precisely the interpolated version of that color variable, which is written out by the vertex shader. So this color variable will change gradually inside the object. This interpolated color variable is assigned to the output variable, which is written into the frame buffer. A 2D camera is responsible for transforming the virtual world to normalized device space, and to specify it we just need a rectangle placed on the virtual world. This rectangle is given by 2 variables, by the center of this rectangle and the horizontal and vertical sizes. We use this W initial letter to denote these properties because they must be interpreted in world coordinates. In the constructor of the camera, these parameters are initialized, and during rendering we need just 2 transformations when it comes to the 2D camera. The view transformation that translates the virtual world in a way that the center of the camera will be the origin, and this is just a translation matrix that translates with the negative center of the camera. The other transformation matrix is the projection, which scales the virtual world in a way that the camera window will be just the square of the edge size is 2, because the corner points of this square are -1, -1 and +1, +1. When the input pipeline is programmed, we will also need the inverses of these transformations. If we maintain the camera transformation in 2 different transformations, like the view and the projection, it's very simple to compute their inverses because of their geometric interpretations. So the inverse of a translation is just a translation with the negative vector, and the inverse of a scaling is another scaling where we use the reciprocals of the scaling factors. Zoom and pan is nothing but the modification of the size of the camera window and the position of the camera window respectively. The camera and the GPU program are global variables because they are used by multiple event handlers and initialization functions. The first object that participates in the virtual world is the triangle. In OpenGL, all objects are vertex array objects, or VAOs for short, and to handle a vertex array object we need an ID. So this ID is going to be this VAO variable. Additionally, we store transformation parameters associated with a triangle object, including scaling factors, the position or a translation, and a rotation angle phi. The creation of the triangle, at least the creation of the OpenGL related part, is here. It's implemented in the create function. So first we ask for a VAO ID and bind that VAO, because these operations will refer to that VAO that has just been constructed. This VAO has two VBOs, vertex buffer objects or arrays. One is going to store the location parameters and the other the color parameters. So first we bind the first vertex buffer object and copy this array to the vertex buffer object, which means that these 6 float parameters will identify positions of the 3 vertices of this triangle object. Then we have to explain to OpenGL how to feed the vertex shader with the data specified in the VBO. So we say that the content of this VBO should be copied to vertex shader input register number 0, and when a particular vertex is considered, 2 floats must be copied to input register number 0. These data are not normalized and the array is tightly packed. For the other VBO, we store the colors associated with the 3 vertices. So this is going to be the first color, which is red, the second color, which is green, and the third color, which is blue. This array is copied to the GPU, and we explain to OpenGL that this data should be connected to vertex shader input register number 1, and for a single vertex, 3 floats should be copied to input register number 1. The animation function of the triangle is responsible for the time-dependent modification or control of the animation parameters. Well, as far as the scaling factors and the position are concerned, these are not modified. However, the rotation angle is set to be equal to the elapsed time t. So we expect a rotating triangle. During rendering, we need the MVP transformation, including the modeling transform that transforms the object from its reference state to its actual state in virtual world, and then the camera's view and projection as steps. Let us start with the modeling transformation. It is also a concatenation of elementary transformations, starting with a scaling that scales with scaling parameters sx and sy in the direction of axis x and axis y. The second transformation is a rotation that rotates around axis z by angle phi, and the third transformation is just a translation where the vector of the translation should be put into the last row of the 4x4 matrix. The modeling transformation first scales, then rotates, and finally translates the point. The draw function of the triangle is shown here. First, we obtain the MVP transformation matrix, which first executes the modeling part. So the object will be placed in the virtual world in world coordinates, and from there we go on with the camera's view and projection transformations to normalize the white space. And this 4x4 matrix is copied to the MVP uniform variable of the shader. We bind this triangle object because in the next step the GL draw arrays function will force that object to go through the pipeline which is bombed just before the GL draw arrays function. Recall that here this binding is really essential because we have two objects, a line strip and a triangle, so we need to know in each drawing phase which particular object should be drawn. So GL draw arrays processes the VBOs from the very beginning and sending 3 vertices through the pipeline, and these 3 vertices define a single triangle. The other object type is the line strip. Here we store as a data member not only the vertex array object identifier, but also the vertex buffer object identifier, because this will be dynamic in this case. Whenever a new click arrives, the new point should be inserted into the VBO. In order to allow this dynamic modification, we also store the clicks or the points on the CPU in this dynamic array called vertex data. Remember that for triangle we had scaling, rotation and translation animation parameters. For line strip we use just a single translation. The create function is as follows. We ask for a VAO and bind it, and now we ask just for a single VBO and bind it. Recall that triangle was represented by 2 VBOs. One stored the vertex coordinates and the second the vertex colors. It is also possible to mix position information with color information in the same array, so we can handle this situation with a single VBO array as well. So here we demonstrate that solution. From this VBO, 2 input registers of the vertex shader are fed. In input register number 0, we will copy the position information. So we copy 2 floats for a single vertex, and in input register number 1, we will copy the color information, that is 3 floats for a single vertex. When the line strip is initialized, we do not really have the definition of these points because the user hasn't started to define the polyline. So there is no copy of data here, but we can still specify or explain to OpenGL how to interpret the data in the VBO, which will be filled just later. As now we store the position information and the vertex information in the same array, a point will be associated with 5 floats. The first 2 floats define the position, and the remaining 3 floats define the color. So when we step from one vertex to the next vertex, 5 floats should be skipped, so that's the stride of the array, and the position information is at the beginning, so it should be accessed with no particular offset, or we can also say that with offset 0. As far as the color information is concerned, the color information comes after the position information, which occupies 2 floats, so when the color information is obtained, we have to use an offset of 2 floats. The modeling transformation matrix of the line strip is here. This is just a transformation matrix for a single translation specified by the wtranslate parameters. The inverse is also easy to obtain. The inverse of a translation is the translation with the negative vector. Add point adds a new click to the current polyline, so that's the way how we can build up this polyline. And recall that in the event handler, the physical pixel coordinates have already been converted to normalized device coordinates, and these normalized device coordinates are sent to here in the add point function. So we use C initialized, standing for clipping space, which is the OpenGL name of normalized device space. The polyline is built in its own coordinate system, and when it is rendered, it goes through the modeling transformation, the camera's view transformation, and finally the camera's projection transformation in order to arrive at normalized device space. Now we have to execute the transformation pipeline in the other direction, because now we have a point in normalized device space and want to know which point corresponds to this in the reference state of the line strip. In order to allow vector matrix multiplication, the normalized device space coordinates are extended by 0 to make it a three-dimensional point and convert from Cartesian coordinates to homogeneous coordinates and multiply with the inverse of the model view transformation matrix. The inverse is just the individual inverses of the individual transformations written in a reverse order. So M vertex is the modeling space point corresponding to the current click. This point is inserted into the vertex data, where the first two floats are used by the XY coordinates and the third, fourth and fifth float position are occupied by the color information. Here we decided to use just a constant yellow color for all vertices. We bind the VBO because the next GL buffer data should refer to that VBO which corresponds or belongs to this line strip, and that VBO is filled up with this array. And the size of the array is increased by 1 in every add point call. Note that here we say that we want our data to be stored in a dynamic draw memory location, which means that not only we want it to be read quickly, but we want to give the possibility to modify it as efficiently as possible. And indeed, we are modifying it at every add point call. Add translation is just modifies the wtranslate parameter of the line strip, and here is the draw. Of course, we don't have anything to do if and there is no point clicked so far. Otherwise, we compute the model view projection transformation as the concatenation of the modeling transformation, the view, and the projection transformation of the camera. This MVP transform is set in the MVP uniform variable of the vertex shader. We bind this line strip and use the GL draw arrays function to force the content of the VBO to go through the rendering pipeline. These points are interpreted as vertices of a line strip. It should be started from the very beginning, and here we specify how many vertices should be drawn. Let's go back to the definition of vertex data for a moment. It stores floats, and we need 5 floats to represent a single vertex. So therefore, the number of vertices is vertex data size divided by 5. We arrived at the point where the discussion was started.